So once again, I want to say a big welcome to all of you here. It's a pleasure to have all of you. Which of you have seen the movie known as A Beautiful Mind before? Can you raise your hand if you have seen the movie called A Beautiful Mind? A Beautiful Mind. A Beautiful Mind. It's good to watch nice movies, though. All right. So A Beautiful Mind is a Freniac. And then he was so smart that he developed a powerful Nobel Prize theorem. Okay. We call it the Nash equilibrium. The man himself is known as John Nash. He developed the Nash equilibrium. All right, so like I said, at this stage, if you want to turn off your this, you can. So in many respects, if you run a business, if you play a football, if you play the game called chess, there is a game theory that is in there. The idea of a game theory is to come out with an optimal result. But you see, in normal games, the best outcome does not mean that another person loses. For example, if you talk about a game, a football game, when one wins, the other loses. Okay. So when you hear the word game, it's like somebody is winning, another is losing. But you're going to see that in a business game, the ultimate situation is that for them to win, they have to cooperate instead of compete. They have to cooperate instead of compete, okay? So what is game theory? It is a branch of economics, especially the microeconomics part. Just as industrial economics is also a branch of economics. But what it does is that it uses mathematical models to analyze situations where firms or human beings, rational human beings, are competing in strategic interactions. And the people behind it are Borel in 1921 and John von Neumann in 1928. These are the people that are behind the game theory. So look at these people on your screen here, and you can see that a lot of gaming is going on. Real gaming. When I say real gaming, your mind will go to what is not a game. But I want your mind to go to what is a game. Because real gaming is going on, isn't it, Francis? Real game is going on. Do you know that in such a game, the people who are playing the game, they don't even have much clue than the people who are watching the game. So sometimes you are outsider, and you, the outsider, you have more clue about the game than the interactions going on. And sometimes you can see the game and see the end of the game before the player sees the end of the game. So this is a game environment. What are the contents of the game environment? Okay. The first thing in a game environment is this. One, you will have players. One, you will have players in the game. Two, you will have strategies. Two, you will have strategies in the game. And three, you will have payoffs. Three, you will have payoffs in the game. Okay. So note, players, strategies, payoffs. And before we take a typical example, I want you to know the difference between cooperative game and non-cooperative game. We've already said that the cooperative game, they are moving together. Non-cooperative games, there are two of them. We have the simultaneous and the sequential. Now, if you can see, simultaneous means that they play it once and that's it. So when you play, you don't know the other person's decision. So when you make a move, you don't know the move the other person will make. Even if you all do it at the same time, okay, you don't know the decision that the other person took. So you can only anticipate the move of the rival. It is sometimes called normal or strategic form game. So note the name, static, simultaneous. The other one, the opposite one, is a sequential, which is a repeated game. Sometimes it's called dynamic. So that when you play the game, the other one plays, and you know the other one play, so you now play, and then he also plays because he knows your play. So they are sequential move games. But that one, it is a moving simultaneously but repeatedly over time. Once again, all of these things might sound like Hebrew to you. The only way you can appreciate this is we look at an example. So let's take the famous classical example known as a prisoner's dilemma, propounded by Albert Tucker. The prisoner's dilemma. Let me see my hands, those of you who have heard about a prisoner's dilemma. Okay. If you have heard about a prisoner's dilemma, raise your hand and let me see. If you have heard about a prisoner's dilemma, raise your hand and let me see. Who is Judah? Who is Judah? So what we are going to do now is that we are going to look at real life situations where you are dealing with a duopoly pricing. A duopoly are two firms that are acting like monopolies. That is a duopoly. For example, you can talk about a Pepsi company and then Coke. If you look at Pepsi and then Coca-Cola, okay, if they come together to determine the price of minerals, then we are talking about a duopoly. So I'm going to use that. So what, the prisoner's dilemma example I'm going to use now is an example of a duopoly. Sometimes you can talk about car sales transactions. Okay. You go to one place and the price of the car is the same because these people are duopolies. All of these are examples of the prisoner's dilemma. So I want you to follow me as I explain the prisoner's dilemma. In the prisoner's dilemma, there are two prisoners. But they're actually not prisoners, they are suspects. One of them is Fuse, and the other is Chia. They have been accused of committing a crime together, jointly. They have promised each other that they are not going to rat on the other person. Okay. In other words, when we are caught, you know how these armed robbers behave. Charlie, when we are caught, you don't know me and I don't know you. Each one is trying to minimize his time in jail. They know that they go to jail, but they want to minimize the time in jail. But in order for the prosecuting courts to actually convict them, they need one of them, just one of them, or even both of them to confess. Because right now, they don't really have evidence to convict them for a long trial, a long jail sentence. So they separate both of them in a different room. No information can pass between them. And you know how these police lawyers do. They start asking them questions. And here is the story. If neither of them confesses, the prosecutor will not be able to convict them of the crime. And all they got to do is to give them 1 year jail sentence. That's it. So remember, confess, and then, no confess. If no confess, 1 year, 1 year. If Husseini confesses and Chia does not confess, you see, so in this case, Husseini is cooperating with the police and Chia does not cooperate, then it means that Husseini will go for free, no jail sentence, because he has confessed. That's what they tell Husseini. They tell Husseini, look, if you don't want any trouble, just confess. And if Chia doesn't, you are free. And then they go and tell Chia the same thing. Chia, confess. If Hussein doesn't confess, you go free. But if both of them confesses because both of them want to go free, then each is going to get an intermediate 6-year sentence. Because now the police have been able to what? The prosecutor has been able to make them confess. And now, bam, we got you. Now you got to make a decision. Each suspect must decide once and for all time, under these circumstances, whether or not to confess. And this is what is known as the conflict of interest situation. Okay. So this is the story. The first thing you want to do in this story is to identify, one, the players, two, the strategies, three, the payoffs. So who can raise a hand and tell me first the players? Who can raise a hand and tell me first the players, the easier part? Who are the players? All right, Christopher.
Doc, please, I think they are the suspects and the prosecutor.
No. Who are the players? Let's go to Aqua Francis.
Look, the players are Fuseni and Chia.
That is it. The players are Fuseni and Chia. Next question. What are the strategies? What are the strategies? Who can tell me? Raise your hand and tell me. It's all in there. What are the strategies? Francis Wyam.
I think the strategy is either to confess or not to confess.
That's it. Those are the strategies. So the strategies are not confess, confess. And then what are the payoffs? What are the payoffs? Don't give me the details of the payoffs, but what are the payoffs? Adolfo.
It's the prison term.
It's a jail sentence. That's it. These are the first questions you will get in the game theory analysis. So in this situation, the players, the strategies, and then the payoffs, you've got to know these. In the story, you've got to know this. That means that you want to read the story well and understand the story well. Okay? Now, next thing. We need to identify whether, and again, I'm going to look here, okay? We are going to represent this whole game in a matrix form. And this is called a strategic or the normal form. Note, representing the game in a matrix form means that you put it in a kind of a box. And I'm going to show that. So you need to put a game in a sort of a box. You need to write a box like this. And then you put a game in a matrix form. And then you write the names of the players. Now, the player, and here we have a row player, and then we have a column player. You see, the row player is the person on the row section here. Okay, let me call it like player one. That's the row player. Okay, and then when we go to the top part, you have player two. That is a column player. Now, in our story, the row player is always the one who was mentioned first. Okay, and if you look at the story, the one that was mentioned first, if you go check it, and I want to take you back there, okay, just so that you are appreciating what is happening here. It's not automatic though. But then, if you look at it, Fuseni was mentioned first. In the prisoner's dilemma, two suspects. Okay? So that is Fuseni. Fuseni was mentioned first. Please, if you are not talking at any point in time, mute yourself. Okay? It always helps. Now, so Fuseni comes first. And so let's go to our drawing. you will give the role player for Fuseni. So it means that this guy is a role player, and that is for Fuseni. And then the top guy, the player 2, the column player, becomes that of what? Chair. So you write chair for this. So that is the first thing that you want to be able to deal with. Any question on that? The second thing, and I want to clean the drawing and then do something different for you to see something. So let's go to the second point. The second point is the strategies. See? The strategies. So you have this box there. You have this second one there. And I'm just rewriting them again for a reason. And then you have this third one there. Okay. And then finally, you have this fourth situation. Of course, I've just done it well. Now, the strategies. Each of them has got a strategy. If you can remember, what are the strategies? The strategies are not confessing and then confessing. Okay, those are the strategies. So we are going to do no confess for the first strategy and then confess for the second strategy. So for this one, we are going to have, so it's split it into 2. Okay. Let me write it first. So this will become, I want to use a different color. This is no confess, and then confess, and then Piatu will have no confess, and then confess. That is how you are going to have this situation here. Now, once you have been able to identify that, of course, you need to create now the final one, which is the payoffs. So you create a box that indicates, that we are going to have these payoffs. If at each point you don't get, let me know. Now, this point of the payoffs is where you got to be very careful. When you are writing the payoffs, you got to be very careful. And why? Because Fuseni's number is a number that comes first, and Pia's number is a number that comes second. So whatever I write in the payoffs, okay, whatever I put in there, the first number here, let's call it A. Use a different color. The first number, that call it A. Okay, that first number is a number for Fuseni. The second number, which is B, is for Chia. So the first number is for the row player. The second number is for the column player. Are you with me? Very good. The first number is the row player. The second number is a column player. So the first number is a row player. The second number is a column player. The first number is a row player. The second is a column player. So now that you have understood how we are going to do the representation, we are going to go to the storyline, and then we will read the story. And this is where you got to understand the story of what is being told. Once you understand the story, you'll be able to put it in that, situation. All right, so let's go to the story, and I want you to pick some key words, key situations in the story. And this was the story. It said that if neither confesses, the prosecutor will give each one of them 1 year, 1 year. And so when you go to not confess section, so let's go to not confess. So in the graph, you see NC, NC. That is a box we are dealing with. Not confess, not confess. What number are we going to write there? What number are we going to write there?
1 1.
1 1. Okay. 1 1. Okay, so you're going to write 1 here, comma, another 1 here. The first one is for who? The first one,
Husseini.
Husseini. The second one is for chair. Okay, let's go to the storyline. And again, if you can remember the storyline, you don't need to go to the storyline. According to the storyline, if both of them confess, what was the jail sentence they were going to have?
6 years.
6 years. Okay, so 6 years. So you don't even need to go and read the story. You can get it there. Now, what I want to do is this. So now you have 6 years. So that means that you need to write 6 for the Husseini guy and then 6 for the chair guy. And then if Husseini confesses, but chair does not confess, which quadrant are we in there? Husseini confesses, chair doesn't confess. We are in this 4th quadrant, isn't it? We are in this section here. We are in this bottom left. What were the values? If Husseini confesses, that is C, confesses. Chair not confess. What value will Husseini get?
Husseini will get 0.
0.
And Chair will get 15.
And chair will get what?
15 years.
15 years. So you write 0 and then 15. And then on the top right, that value will change, isn't it? On the top right, you have 15. Because in this case, Chia is rather confessing. Husseini is not confessing. Okay? Chia is confessing. Husseini is not confessing. So Chia will get 0 years. Because Chia is always a column number. And Husseini is going to get 15 years. And I want you to see these 15 years as jail sentence. So the higher the number, the worse your life is. The lower the number. Okay. So I want you to see that. I could have added negatives to them. And I just want you to see that in this context, higher values are not good because it's a jail sentence. This is what we call representing the whole thing in a matrix form, in a strategic form, in the normal form. Could you have done this? That is how you represent this story. So represent this whole thing, this game theory situation in a matrix form. This is how you do the representation. And you need to know the details. You need to actually give the details. So for example, these are some of the details. If Husseini confesses and Chair doesn't, Husseini gets 0 sentence, Chair gets 15. If Husseini confesses and Chair does, both will get 6 years. If both don't confess, they both get 1 year. So these are the details. You got to learn how to represent games in the matrix form, in the matrix form, in the matrix form. You got to learn how to do that. Now, first question that you should note about this. Is there a pure strategy Nash equilibrium? That is the first question that you want to note in here. Is there a pure strategy Nash equilibrium? Now, before I answer that question, I want you to note that there are several kinds of equilibria definition. There are several kinds, and I want you to take note of them. The first one and the easiest one is known as the dominant strategy equilibrium. Take note. The dominant strategy equilibrium. The dominant strategy equilibrium. The dominant strategy equilibrium. Now, before we talk about the dominant strategy equilibrium, I want to show you something here. I want you to understand the meaning of dominance. Dominance. What is a dominant strategy? And what is a dominant strategy equilibrium? What is a dominant strategy? And what is a dominant strategy equilibrium? Now, a dominant strategy, and I want to say a dominant strategy, we are talking about a strategy for the player, either the role player, Husseini, or the column player, Chair. A dominant strategy. What is a dominant strategy? A dominant strategy is that sort of strategy you're going to stick to. It doesn't matter what the other player does. You are going to stick to that strategy, come what may. That's a dominant strategy. It's a strategy that you are not going to change, okay? No matter what the other player does, you're going to stick with that strategy at all times. Let me give you a typical example. Let's go to the story. Look at the strategy for Fuseni. Guys, how many strategies does Fuseni have? Quickly, how many strategies does Fuseni have?
He has 2.
How many strategies does Chia have?
Also 2.
Good. Now, for you to know whether or not each has a dominant strategy, this is what you do. Look at the row section here. If Fuseni should go for non-confess, all right, the question you ask yourself is that, what will Chia do? Now, watch it. If Fuseni, and again, I'm not interested in Fuseni, I'm interested in Chia because I'm interested in what he's going to do. If Fuseni should go for NC, we are in this row. We are in this row now. If Fuseni should go for NC, that is the row we are in. Okay, we are in that row. If Fuseni should go for NC, we are in this section. What do you think Chia must do? Well, Chia has 2 options. Chia can also go for NC and get 1 year jail sentence, or Chia can go for C, confess, and get 0 years sentence. Which one do you think Chia will go for? NC or C?
C.
C. Because 0 years is better than 1 year. Now, keep that in your mind that Chia has gone for C. And then let us allow Fuseni to change his strategy from NC to C. So now we are in the bottom row. Fuseni is now going for C. Let us see whether Chia maintains his C. So if Fuseni should now go for C, Chia has a choice of choosing NC and getting 15 years. Remember, the second number is for the column player. Or Chia has a choice of choosing C and getting 6 years. Which one would Chia go for?
He still remains with C.
Exactly. So by maintaining the C throughout, irrespective of what Fuseni did, we can say that Chia now has a dominant strategy. A dominant strategy is a strategy you stick to no matter what the other player does. Is that clear, ladies and gentlemen? Is that clear? Okay. You want to be able to understand this. So note what a dominant strategy is. Your strategy is dominant if you maintain that strategy. But there are 2 things that I want you guys to note here. There are 2 things. There's something that we called a dominating strategy, dominating, and then dominated. Dominating, and then dominated strategy. Now, a dominated strategy becomes a strategy that you will not go for because there's a better strategy than that. A dominating strategy is a strategy you will go for when compared with another strategy. You guys get it? Of course, if you don't get it, you'll always ask a question. So I want you to keep that in mind, and then we go, and then I'll ask you some few questions very quickly. Okay. Now, anytime, so there's a difference between dominated and dominating. Okay. So I want you to look at this strategy. Look at player 1. I'm going to do a rough estimate of something. Look at player 1. Player 1 has a strategy T and B. Look at player 2. Player 2 has a strategy L, left and right. Player 1 has a strategy top, bottom. Now, if you look at the numbers I have written down, guys, it is for which player? And why do you say so? If you look at the numbers that I've written, the payoff matrix, the payoffs, It is for which player? And why do you say so?
I think it's for player 1.
Why do you say player 1?
And it's because the first number in the list of numbers.
And then the second number is what?
For the player 2, unknown anyway.
Good, good. So the second number are not shown. That is for player 2. The first number are shown. Well, in this case, you can see that I've given you a slight clue. I've given the numbers to be red. And the player 1 is red. Player 2 is black. So red is, there's a clue that this is for player 1. Okay, now keep that in mind. If you look at player 1, it's got strategy top and strategy bottom. Okay, so let's say that player 2 select left. All right, which strategy? And again, I want you to see these values now as higher is better. If you look at this strategy, if player 2 should select left, that's how you say it. You assume what player 2 does before you now analyze the strategy of player 1 in this context. If player 2 should choose left, what strategy will player 1 take? If player 2 should play left, what strategy will player 1 take?
Player 1 would take top
Good. Why?
because 1 is higher than 0.
Correct. If player 2 plays right, player 1 will take what?
You still take top.
So
because
does player 1 have a dominant strategy or it doesn't? Francis?
Yes, player 1 has a dominant strategy
Why do you say so?
because he sticks to his strategy no matter what the other player does.
That is correct. So he's still maintaining the top. And as long as he's maintaining the top, irrespective of what player 2 is doing, player 1 got a dominant strategy. So we can say that the strategy bottom is dominated strategy. Why? Because I'm talking about just 2 things, top and bottom. But if there were 3, we'll come to that one. So if you compare top and bottom, top is a dominating strategy and bottom is a dominated strategy. So B is a dominated strategy. Do you get it? So you got to know the difference between a dominated strategy and a dominated strategy is the one you don't want to go for. And again, we're not talking about the payoffs. We're talking about the strategy. Just that the payoffs will guide you to know whether the strategy is dominated or not. This is a dominated strategy, B. So what is the dominant strategy for Fuseni? We have seen that the dominant strategy for Fuseni is to confess. Do you remember? Oh, you don't. The dominant strategy for Fuseni is to confess. Do you remember? Fuseni was to confess.
Yes.
Yes.
Good. Now, it will be the dominant strategy for Chia? Who can analyze that? Looking on the screen here. Who can walk us through the dominant strategy for Chia? Fuseni's dominant strategy is, sorry, did I rather look at Chia's strategy? Anyway, Fuseni's dominant strategy is this, confess. Okay. What is Chia's? Does Chia have a dominant strategy? Who can walk us through?
He also has to confess.
And walk us through that, because once you conclude, it means you can walk us through that.
Okay.
Mm-hmm.
So if you have to keep Fuseni's strategy at confessing, if Chia decides not to confess, he gets 15 years. If he decides to confess, he gets 6. And in this case, 6 is better than 15.
Okay.
Yeah. And then
continue.
Yes. And then if Fuseni decides not to confess, and Chia also decides not to confess, he gets 1. If he decides to confess, he gets 2. He gets 0. And 0 still remains better than 1. So in instances, whether Fuseni chooses to confess or not to confess, Chia's best dominant strategy is to confess.
Thank you. That's it. How you analyze it is what I want. Okay, in an exam situation. So Chia has a dominant strategy, which is confess. Husseini, we know, already has a dominant strategy, which is confess. Both of them have got dominant strategy. They will play it. They will play it till thy kingdom come. So we now have an equilibrium. And so in this case, the equilibrium in question, the pure strategy Nash equilibrium, and this is the way I write it. The pure strategy Nash equilibrium here is a dominant strategy equilibrium. The dominant strategy, so because both of them have got a dominant strategy, they are going to play it. They are going to play it. Irrespective of what the other does, they are going to play it. And therefore, we have a dominant strategy equilibrium. The first and the easiest equilibrium, the first and the easiest Nash equilibrium is the dominant strategy equilibrium. And they will play it. They will play it. They will play it because it is their dominant strategy. They will play it. So on the basis of that, we can then conclude that both players have got what? Dominant strategy. That was a question here. Check if the prisoners, each prisoner has a dominant strategy. And what you explained is what is here. And then when you check the others, you see that, yes, each of them has got a dominant strategy. Well, then the next question is that, do we have a pure strategy Nash equilibrium? Yes. The pure strategy Nash equilibrium, according to John Nash, and again, when you read this, you might not fully understand, is the best response behavior. And the best response behavior for Chia is confess. The best response behavior for Husseini is to confess. And so their pure strategy Nash equilibrium happens to be a dominant strategy equilibrium. If each player is satisfied with his choice, given the other person's choice, fantastic. Then we have a pure strategy Nash equilibrium. Now, it is said to be the solution that will appeal and that will seem sustainable from all the players, okay, which all the players are choosing their best strategy, given the actions of the other player. So you choose your best, make sure your best is your best. I will choose my best. If your best and my best are dominant strategies, then our dominant strategy equilibrium becomes a pure strategy Nash equilibrium. Okay, so watch something here. The pure strategy Nash equilibrium, you can achieve it through the dominant strategy equilibrium. That is when both have got what? Dominant strategy. So when both have got a dominant strategy, we call the pure strategy Nash equilibrium a dominant strategy equilibrium. But of course, what if both don't have a dominant strategy? That's what we are going to. Okay. So get some few terminologies right. A dominant strategy equilibrium is always a pure strategy Nash equilibrium. Those are the three approaches to arriving at the pure strategy Nash equilibrium. One of the pure strategy Nash equilibrium is when we have a dominant strategy equilibrium. So the dominant strategy approach can help you arrive at a pure strategy Nash equilibrium. What is the second approach? The second approach is known as an iterative elimination of strictly or weakly dominated strategy. Iterative elimination of strictly or weakly dominated strategy. Don't worry, we are going to look at that right now. And then the final one is known as the best response strategy. The best response, that one is lovely. The best response strategy. So the pure strategy Nash equilibrium in this prisoner's dilemma is confess, confess. We've already established that. And that will lead to 6 and 6 for each player. Now, before we move on, let's look at something known as Pareto efficiency or Pareto optimality. And I want to quickly mention that before we move on. What is, and again, if you are not getting something, let me know. Please remember, we have looked at the dominant strategy approach, which helps us to achieve the pure strategy Nash equilibrium. Don't forget that. There is another approach you can use to achieve the pure strategy Nash equilibrium, which is not a dominant strategy approach. It is called iterative elimination of weakly, strictly dominated strategy. We are going to look at that. I'm coming. We'll do that. Then there's a final one, which is the best response approach. We are going to look at that as well. But before we look at that, there's something you need to understand, which is the concept of Pareto optimality. And there's always a question on that. What is Pareto efficiency? Well, Pareto efficiency is an outcome. So let's say you have an outcome. That outcome is said to be Pareto optimal or Pareto efficient if there is no outcome that Pareto dominates it. So let me give you a couple of outcomes. They will help you to appreciate this better. Okay. So let me give you an outcome. For example, each of the items you see here are outcomes. 1 and 1 is an outcome. 0 and 15 is an outcome. 15 and 0 is an outcome. 6 and 6 is an outcome. Okay. All of these are outcomes. When is an outcome Pareto optimal? Let's take an outcome called outcome O. And this outcome O has got two numbers, 7 and then 8. Okay, that is our outcome O, 7 and 8. And let's take another outcome called O prime. Okay, outcome O prime. And this outcome O prime has got some coordinates, and the coordinates are 7 and then 2. I'm going to compare the two and find out which one is Pareto optimal. Which one? Now, if you look at the content of outcome O, we are dealing with 5 units of utility. Remember that the 7 is for the player 1, and then the 8 is for the player 2, right? So player 1 has got 7 units of utility, and player 2 has got 8 units of utility. If you look at that outcome and you compare that outcome with O prime, you can see that still in O prime, player 1 has 7 units of utility, but player 2's utility has gone down. It is not 8, it is 2. So which of the two outcomes is higher? Is it O or O prime? Combined wise, which of them is higher?
That will be O, sir.
Oh,
That will be O.
Right.
Now, the word optimality or Pareto efficiency deals with society. So it deals with all of us. It's not private efficiency, it's public efficiency. So it is where both of us are benefiting. So when both of us are benefiting, then you have what? You have that optimality. Now, let's go and take both of them. If you look at outcome O, combining the outcome of O and the outcome of O prime, you will notice that outcome O is at least as good for everybody than outcome O prime. Do you realize that? For everybody. O is at least as good for everybody than O prime. So if you look at O, okay, player 1 is going to get 7. Player 2 is going to get 8. Now, when you get to O prime, player 1 could have said that, oh, I'm indifferent between the O and O prime. Do you realize that? Do you realize player 1 can say, I'm indifferent between O and O prime? Do you realize that?
Yes, sir.
Why? Why do you realize that?
Because in both situation, he has the same satisfaction. So
Exactly.
he can choose
Which is
any
what?
which is the 7.
Exactly. So player 1 can say that I'm indifferent. I can choose O, I can choose O prime. But we are looking at efficiency for everybody, Pareto. We are looking at optimality for everybody. But you can see that player 2 will never say that. Player 2 is going to choose which one? O, because 8 is better. So now, collectively speaking, we will say that O is better. That's what we mean by at least. At least. So it is in this context we say that, listen carefully, that player 1, okay, the player 1, even though he's indifferent, collectively speaking, outcome O, Perito dominates outcome O prime. Outcome O, Pareto dominates outcome O prime. You get it? If you don't get it, I'm going to give you another example. Okay, let me give you another example. Let me add another example to it. Let me call this one A, and then the A, let me do 4 and 8. 4 and 8. I'm going to compare between A and O. Which outcome Pareto dominates the other? A and O. You can tell me. Which outcome Pareto dominates the other? A and O. A and O. Which outcome Pareto dominates the other? Francis?
The O dominates the A.
Don't say O dominates the A. Say O Pareto dominates A.
O Pareto dominates A, sir.
Good. And I agree with you. Now, let's come to A and O prime. Which outcome Pareto dominates the other? A and O prime. Which outcome Pareto dominates the other? This is the outcome, and this is the other. Which outcome Pareto dominates the other? Miriam. Kobna.
Oh, Perito dominates the O prime.
I was very specific, Miriam. I was asking between A and O prime. That was my question.
Yeah.
A Perito.
Oh, Miriam, go ahead. Miriam, go ahead.
A Perito dominates O prime.
A Pareto dominates O prime. That is wrong. If you look at A is good. Okay, player 1 is okay. Player 1 will be happy because 8 is better than what? 2. So sorry, player 2 is going to be happy for that. Player 2 is going to prefer the A to the 2. Okay, prefer the 8 to the 2. But when you look at player 1 will not prefer 4 to 7. So neither A and O prime Pareto dominate each other. Non-Pareto dominates each other. Okay, you are good in terms of the second one. I am good in terms of the first one. So there is no Pareto domination between A and O prime. There is Pareto domination between A and O. O Pareto dominates A. O Pareto dominates O prime. But A and O prime do not Pareto dominate each other. Guys, you get it. This is very important. This is crucial. This is very important. So let me give you a couple of examples. Okay, now that you get a picture here. I'm going to give you thinking examples, and you got to be able to get it. Question 1. Can a game have more than one Pareto optimal outcome? Can a game have more than one Pareto optimal outcome? I want you to understand the principle of Pareto optimal. Look at the one I just showed you. There were only 3 outcomes. And then look at that whole game, the one I just showed you. Can a game have more than one Pareto optimal outcome? Look at the A, the O prime that I've just shown you. Can a game have more than one Pareto optimal outcome? Ivy.
Sir.
Yes or no? Can a game have more than one Pareto optimal outcome?
With our example, no, sir.
No. Okay. Miriam.
No, sir.
No, sir. Okay. Christabel.
Doc.
Don't call me. You just answer.
I'm not too sure.
That's why you were calling me.
Yes.
Okay. All right. Let's go to YM. Francis. Can a game have more than one Pareto optimal outcome? Look, let me take you back here, and then you appreciate it. Look at this game. We had outcome A, outcome O, and then outcome O prime, isn't it?
Yes,
So
sir.
can a game have more than one Pareto optimal outcome? Just using this example. How many Pareto optimal outcomes did we get here?
We got
Two.
one, sir.
We got two.
We got two.
We got two. When we compare the A and then the O, we realize that the O Pareto dominates A. All right? We realize that O Pareto dominates A. And then we realize that O Pareto dominates O prime. But we realize that these two, they do not Pareto dominate each other. Wait, if I had brought another one, come on. For you to Pareto, let me tell you why it is. Yes, you can have more than one Pareto optimal. And this is the reason. So this is a yes. If all the payoffs of two outcomes are the same, neither will Pareto dominate each other. So let's take a situation like this. And then you have, and again, it doesn't matter how many are put here. Let's say that the payoffs for this are 2 and 4. And then the payoff for this are also 2 and 4. Which one will Pareto dominate the other? Which one? None.
Look, they are indifferent.
Not indifferent. Which of these two outcomes, let's say that this outcome is A and this outcome is B, which of the two outcomes will Pareto dominate each other?
None of them.
Now listen, when none of them Pareto, dominate the other, then it means that they are both Pareto optimal on their own. If none of them Pareto see, for Pareto domination, okay, is when you have something that at least I don't have. So once you can say that you have nothing that is more than me, at least that is more than me, then I am Pareto optimal on my own because nobody is champion than me. As long as I cannot be Pareto dominated, I'm Pareto optimal. Write that down. Write that down. As long as you cannot be Pareto dominated, you are Pareto optimal. For you to be Pareto non-optimal, you've got to be Pareto dominated. For you to be Pareto non-optimal, you've got to be Pareto dominated. Or what? Yeah, you got to be Pareto dominated. But as long as you are not Pareto dominated, you are Pareto optimal. Does it make sense? Because I'm coming to ask you another question. Okay, let's go to the next question, if you get it. The next one. Next question. Does every game have at least one Pareto optimal outcome? Now, I want you to understand what I just said some few minutes ago. For you to be Pareto optimal, you must either dominate another, but you must not be dominated. You dominating another is irrelevant, but you must not be Pareto dominated for you to be Pareto optimal. For you to have a Pareto optimal outcome, you must not be Pareto dominated. So the question is that, does every game have at least one Pareto optimal outcome? Now, if you have one Pareto optimal outcome, it means that you are not Pareto dominated by anybody. But for somebody to Pareto dominate you also makes that other one Pareto optimal. So, does every game have at least one Pareto optimal outcome? Of course, if you say yes or no, I will ask you why. I know what something is happening. Some of you, your brain is singing, is dwindling, singing, okay? Let me call you Francis. I see you.
Yes, sir.
What is your answer to this? You came late.
My answer is yes.
Explain.
Because as you said, for you to be Pareto optimal, you need to be Pareto dominated. So at least one of the games should have a Pareto dominated.
Hmm? Say that again.
I'm saying that for you to be Pareto optimal, you are to be Pareto dominated. So at least one of the games should be Pareto dominated.
One of the games to be. The question was, does every game have at least one Pareto optimal? So I think your last sentence should be, so at least one of them should be Pareto optimal.
Yes, sir.
Yeah, one of them has to be or must have a Pareto optimal outcome. Because for you to have a Pareto optimal outcome, you must Pareto dominate another, okay, which is Pareto dominated then. Okay. And so if you have a game, let's say that nobody is Pareto dominated. Okay. Nobody is Pareto dominated. The word Pareto dominated, for you to know that nobody is Pareto dominated, then it means that you know very well that, you know, somebody has a Pareto optimal outcome. Okay. So that is how you have explained it, but you have said it, but then the explanation is it. So here's the answer. Every game has to have at least one Pareto optimal outcome, at least one. Why? This is because in order not to be Pareto optimal, it has to be Pareto dominated by another anyway. If you tell me that I am not Pareto optimal, then it means I'm Pareto dominated. Okay, so if you tell me that I am Pareto optimal, okay, or I have a Pareto optimal outcome, then it means that I am not Pareto dominated. Yeah, you cannot dominate someone and then that person cannot be not Pareto dominated. And that is why it is a yes. Let me go to the next one. Let's go to the prisoner's dilemma. I'll come back to the prisoner's dilemma, but I watch something. And again, this point, you may not fully understand. When we go further, you will understand. The pure strategy Nash equilibrium, it doesn't have a Pareto efficiency. It does not have a Pareto optimal outcome. And why? And again, remember the prisoner's dilemma. In the prisoner's dilemma, do you realize that the pure strategy Nash equilibrium was confess? Do you remember?
Yes.
Okay. Now, if we go and check, and let me see whether I can get that here. Yes. If we go and check, let's check whether there's a Pareto optimal outcome here. Let's go and check whether there is what? A Pareto optimal outcome. And you will appreciate something here about Pareto efficiency or Pareto optimality, and then pure strategy Nash equilibrium. Follow me here. Is there a Pareto optimal outcome in the prisoner's dilemma? And check whether that Pareto optimal outcome is the one that is a Nash equilibrium or not. By the way, do you all remember that the Nash equilibrium was 6-6? Confess. You remember?
Yes.
Okay. Now let's check each outcome one by one. Look at outcome 1-1. And so for you to check it, you have to look at it and ask yourself which one Pareto dominates it. So 1-1. Let's compare that with all of them one by one and see which one Perito dominates 1-1. Okay. 15 and 0. Okay. If you compare that with 15 and 0, okay, you will see that 1 is better. The red one is better than 15. All right. And the 0 is better than 1. So you can see that 15 and 0 does not Pareto dominate 1-1. Do you see that? Do you see that? 15-0 doesn't Pareto dominate 1-1.
Yes, sir.
Do you hear me?
Yes, sir.
Okay,
Yes,
let's go
sir.
to 0 and 15. Does 0 and 15 Pareto dominate 1, 1?
No, sir.
No. Let's go to 6, 6. Does 6, 6 Pareto dominate 1, 1?
No, sir.
So since nobody Pareto dominates 1, 1, we can say that 1, 1 is what? Pareto optimal. Does it make sense now?
Yes.
Okay, let's go to, so 1, 1 is Pareto optimal. Let's take that. Okay, done. Let's go to 15, 0. I'm now going to circle 15, 0 and then check if anybody in some way Pareto dominates 15, 0. So 15, 0, let's check 1, 1. Does 1, 1 Pareto dominate 15, 0? Does 1, 1 Pareto dominate 15, 0?
No.
Huh?
No, sir.
1, 1 does not Pareto dominate 15, 0. Why? Because even though this 1 is better than 15 in terms of jail sentence, this second 1 is not better than the 0. So together, remember optimal, together 15, 0 is not Pareto dominated by 1, 1. Let's check 0, 15. Does 0, 15 Pareto dominate 15, 0? No.
No.
Does 6, 6 Pareto dominate 15, 0?
No, sir.
Exactly. So none of them Pareto dominate 15, 0. And therefore, we can say that 15, 0 is Pareto optimal outcome. Boom, we have that sorted. Let's go to 0, 15. You're going to find something interesting. 0, 15. Let's start with 1, 1. Does 1, 1 Pareto dominate 0, 15?
No, sir.
Oh,
No, it doesn't. Because this 0 is better than the 1 somewhere. So that's out. Does 15, 0 Pareto dominate 0, 15?
no.
Does 15, 0 Pareto dominate 0, 15?
No, sir.
No. Does 6, 6 Pareto dominate 0, 15?
No, sir.
No.
Therefore, we can say that 0, 15 is Pareto optimal. Now let's go to 6, 6. Let's start with 1, 1. Does 1, 1 Pareto dominate 6, 6?
Yes.
Yes, straight away, we have no doubt about it. Therefore, we can say that 6, 6 is not Pareto optimal. Therefore, we can say that how many Pareto optimal outcomes are in this prisoner's dilemma?
Doc, 2.
No, it's not 2.
Three.
You're not following.
It's
How
3.
many Pareto optimal outcomes are here?
3 Pareto
It's
optimal
3.
outcomes.
I mean, if you are following, if you are seated and your eyes glued towards me, you will know that I've already taken them. And you will know that these are the 3 Pareto optimal outcomes because nobody Pareto dominates it. As long as 6, 6 is Pareto dominated, 6, 6 is not a Pareto optimal outcome. Now watch, 6, 6 is not Pareto optimal. However, do you remember that 6, 6 was a pure strategy Nash equilibrium? You remember?
Yes.
So in the prisoner's dilemma, and again, it's only in the prisoner's dilemma this happens. In the prisoner's dilemma, okay, the pure strategy Nash equilibrium has no Pareto optimal outcome. It is not a Pareto optimal outcome. And I need to ask you the question, why? And again, the why is here. The reason why the pure strategy Nash equilibrium fails usually to imply Pareto optimal outcome or Pareto optimality or Pareto efficiency is that in games, there are many externalities that the players fail to internalize. And so when you go to this one, because there was the tendency to cheat, that is why they ended up 6, 6. You know, the best outcome would have been for them to go for 1-1 jail sentence. That is each one keeping quiet, not ratting on the other, and not confessing. And the prosecutor had no choice but to give each one of them 1 year jail sentence. But Fuseni knows the lifestyle of Chia. Fuseni, he is aware that Chia has been my buddy, and for over the years, I know how criminalized this guy is. His mind. Even if we agree, he will go and rat on me. I know him and I know his family and his entire generation. And so I will not sit down to be fooled. And so I'm going to confess. Watch. He decides to confess. He had a dominant strategy. He decides to confess. Boom. And then Chia also thinking like him because they are all of birds of a feather. Chia will also think, so he also decides to confess. And eventually, boom, they all end up 6 years. The prosecutor was aware of this. And he puts them in that tight corner. But if they were honest, but they are not honest in the first place, okay? They are thieves. Come on. Honesty is not in their brain. And so they decide not to go for the don't confess and get a 1 year, but they rather go for the confess, which was the best outcome for them. And then that is not Pareto optimal. Why do we say it's not Pareto optimal? Because it doesn't benefit each other. Remember, Pareto optimality is when we both together benefit. Ouch. It is not a private resource. It is a public resource. It is not a private benefit. If you look at this 1-1, it is a private benefit. But then, sorry, if you look at this 1-1, it's a public benefit, but this one is too private. They are all being selfish. So none of them benefited from the 1 year jail sentence. They rather got a 6 year, and which is not Pareto optimal. It's not a sensible outcome. But it's come out. It is come out because it's not sensible. It's not optimal. It's not societally friendly for each one of them. And that is why the prisoner's dilemma is not a Pareto optimal outcome because of the tendency to cheat. So the Pareto optimal outcomes were the ones we explained here. And you can see that the success is not a Pareto optimal. It's not good socially. Okay. It is strictly dominated by 1-1. You can see that strictly. If you go to the other one, it is weakly dominated by the other two, but at least it's strictly dominated by 1-1, even though it's weakly dominated by the 0, 15, and 15-0. Right. So interestingly, the prisoner's dilemma is not a Pareto optimal, okay? And that is a paradox of the prisoner's dilemma. The best outcome would have been for them not to confess, but there is that tendency to cheat. So they end up confessing, which led to that bad situation. Now, I'm going to ask you some quick questions here. Get ready. Open your brain, open your cerebellum, open your cerebrum and the medulla oblongata. And I'm going to ask you which of these payoffs is a Pareto optimal outcome in these 4 games. You're going to take each game, you tell me whether it's a Pareto optimal outcome or it's not a Pareto optimal outcome. So let's go to 1-1. Look at the first one. We're just looking at this first game. Okay, this first game here. Just look at this. Okay, left, right, and all of that. Okay, so look at outcome 1-1. Is it Pareto optimal? And again, here higher is better. I want you to look at this as higher is better. So is 1-1 Pareto optimal outcome?
Yes, sir.
Why do you say so?
Because collectively, both of them are better off.
So if you compare 1-1 with 0-0, 1-1 is better, isn't it? Or let me put it this way. 1-1 is not Pareto dominated by 0-0. 1-1 is not Pareto dominated by the second 0-0 on the bottom left. And 1-1 is also not Pareto dominated by 1-1. So we can say that this corner here, the top left corner here, is what? It is Pareto optimal. And if that one is Pareto optimal, then this one here is also what? Pareto optimal. As for the 0-0, believe me, they are all Pareto dominated by the 1-1. So how many Pareto optimal outcomes are in this first game? How many Pareto optimal outcomes are here?
Two.
How many?
I think there are two.
Two, and that's it. That is it. You can see the answer here. Let's go to the next question. You have 2, 1, 0, 0, 0, 0, 1, 2. Which outcome is Pareto optimal? Take them one by one. Take 2, 1. Is it Pareto dominated by 0, 0?
Nope.
Is it Pareto dominated by the next 0, 0?
Nope.
Is it Pareto dominated by 1, 2?
No.
No.
So 2, 1 is Pareto optimal. Okay. Let's look at 0, 0. Is it Pareto dominated by 2, 1?
Yes.
Yes.
Yes. So 0, 0 are Pareto dominated, so they are not Pareto optimal. 1, 2. Is it Pareto dominated by, I know it's not Pareto dominated by 0, 0. So let's see. Is it Pareto dominated by 2, 1?
No.
So how many Pareto optimal outcomes are here?
2.
Which are they? That's it. 2, 1, and then 1, 1. So 2, 1, and 1, 1 are Pareto optimal. That's why you see them circle. Are you following?
Sir, you said 2, 1, and 1, 1?
Sorry, 2, 1, and 1, 2. Okay. Those ones that have been circled, they are the Pareto optimal outcomes. Let's go to the next one. Okay. The next one here is at the bottom. Head and tail, head and tail. Let's look at 1 and negative 1. This 1 and negative 1, and then negative 1 and 1. Is it, this is beautiful. A 1 and negative 1, is it Pareto dominated by negative 1 and 1?
No.
Is it Pareto dominated by this second negative 1 and 1?
No. No, please.
Is it Pareto dominated by itself, 1 and negative 1?
No.
Okay. So on the basis of how many Pareto optimal outcomes do you think we will have here?
All of them.
All of them.
Oh.
All of them are Pareto optimal because nobody Pareto dominates the other. Okay. And so that is your answer at the bottom here. That is it. All of them are Pareto optimal. All of them are Pareto optimal. Let's go to the last one. Last one. Okay. Last one is at the bottom right. C and D, and then C and D. Negative 1 and then negative 1. Is it Pareto dominated by negative 4 and 0?
No, please.
Is it Pareto dominated by 0 and negative 4?
No.
Is it Pareto dominated by negative 3 and negative 3?
No.
So negative 1 and negative 1 is Pareto optimal. Fine. Let's go to negative 4 and 0. Negative 4 and 0, is it Pareto dominated by negative 1 and negative 1?
No.
Is it Pareto dominated by 0 and negative 4?
No.
Is it Pareto dominated by negative 3 and negative 3?
No.
So negative 4 and 0 is also Pareto optimal. What about 0 and negative 4? Don't go through it. Straight away, it is what?
No.
Pareto optimal.
Optimal.
Let's go to negative 3 and negative 3. Negative 3 and negative 3, is it Pareto dominated by negative 1 and negative 1?
Yes.
Finished. Therefore, negative 3 and negative 3 is not Pareto optimal. This one reminds you of what? Who can tell us? This last one, it reminds you of what?
The PSME.
Well, it reminds you of something, the prisoner's dilemma.
Okay.
That is how the prisoner's dilemma is. If you go and check, the PSNE is negative 3, negative 3. But it is not the Pareto optimal outcome. All of them are Pareto optimal. So here, how many Pareto optimal outcomes are here?
3.
3.
3. There you go. Okay. Wow. So you should learn how to identify Pareto optimal outcome. Anytime you have one matrix drawn, you should be able to answer that in that game, in that matrix, which outcome is Pareto optimal outcome. And the way to define a Pareto optimal outcome is that it's not Pareto dominated. It is not Pareto dominated by any. Even if it is Pareto dominated by 1, it is no longer Pareto optimal. All right. The next point to look at is a quick one. It's called a zero-sum game. You may have heard a lot about the zero-sum games, zero-sum game. The question is that we need to first of all understand a zero-sum game and then understand whether the prisoner's dilemma is a zero-sum game. See, I can give you any matrix and I ask you, is it a zero-sum game? Okay, it's not just the prisoner's dilemma. How do you know whether or not it's a zero-sum game? Simple. Understand what a zero-sum game is. A zero-sum game is when one man's meat is another man's poison. That's how we used to know it. A zero-sum game. That is when one man's meat is another man's poison. Take, for example, one person's gain is exactly the other person's loss. Poker, chess, contract. 2 people cannot win the contract. One got to win, the other got to lose. And so when you sum the values together, we have a constant value or 0. So one person wins 3,000. The other person will lose the 3,000. If you sum the 3,000 with a negative 3,000, you will get a 0. Zero sum game. Are you with me? Are you following?
Yes, sir.
But it's not necessarily going to be 0 all the time. Sometimes, if you sum the 2, it leads to a constant value, and that constant value keeps happening. Okay, it doesn't change, and that is why we say it's still a 0 sum. But most of the case is going to be actual 0, depending on what you're looking at. So, is the prisoner's dilemma a 0 sum game? Remember, when you sum the outcomes, they end up with what? 0. Let's go to the chart that we drew for this prisoner's dilemma. Look at the prisoner's dilemma here. Okay. Look at this prisoner's dilemma very carefully. Okay. Look at it. Now, if you sum 1 and 1, what do you get?
2.
2. Let's see whether there's constant. If you sum 15 and 0, what do you get?
15.
If you sum 0 and 15, what do you get?
15.
If you sum 6 and 6, what do you get?
12.
Is the prisoner's dilemma a 0 sum game?
No, please.
No prisoner's dilemma is a 0 sum game. Come on, this is the meat. This is the meat of the game. This is the meat of the situation. Okay, so let me show you. I'm just showing you quickly. Okay. So the prisoner's dilemma is a non-zero sum game. One player's gain is not exactly the other player's loss. Watch something. Okay, watch something. Do you remember the game that we did? Okay, the one that we looked at here. Which of the games here is a 0 sum game? Check carefully. We have 4 different games. Okay, let me show you how you can identify them. So the 4 different games, this is number 1, this is number 2, this is number 3, this is number 4. Which game is a 0 sum game here?
Number 4.
Number 4, that's it. Number 4 is a 0 sum game. The rest are not 0 sum games. Have you heard of the rock, paper, scissors? Have you heard of the rock, paper, scissors game?
Yes, sir.
0 sum game?
Yes.
Yeah. It's a 0 sum game. It is a 0 sum game. Okay. That is a rock, paper, scissors. Take me. So I want to talk about 0 sum games. Those are what I mean by 0 sum games. All right. I told you that there are 3 ways of arriving at the pure strategy Nash equilibrium. The first way of arriving at the pure strategy Nash equilibrium, I told you, was the dominant strategy approach. Do you remember? where both players have got a dominant strategy. But then I told you, what if they don't have a dominant strategy? Well, if they don't have a dominant strategy, then you can use iterative elimination of weakly or strictly dominated strategy. And I said, we'll look at that one. So let's quickly look at that. That is a second way you can use to arrive at a pure strategy Nash equilibrium. What if there was no dominant strategy equilibrium? Remember, Fuseni had a dominant strategy. Pierre had a dominant strategy. Both have a dominant strategy. That guy got a dominant strategy equilibrium. All of the players have dominant strategies. But what if not all of the players have a dominant? What if one has a dominant strategy, the other does not? Or what if none of them have got a dominant strategy? Well, then you will have to use the eliminating, the strictly iterative elimination. The word elimination is deletion. Strictly dominated strategy. Repeatedly. Or you can use the best response strategy and combining the two of them. Those two approaches could be used to arrive at a pure strategy Nash equilibrium. When you cannot use a dominant strategy approach. And this is based on the common knowledge of rationality. Let's take a typical example. You have the United and American Airlines here. They are flying 96, 64, and 48,000 passengers between Chicago and Los Angeles every quarter. That is how much they fly. The United Airlines, okay, the number they fly are what you see here, 96,000. That is a quantity they fly. 64,000 and then 48,000. The American Airlines is player 2. They fly 96, 64, and 48 at the same time, like that. But what are the payoff? Okay? If United should fly 96, he is going to get either $3.1 million or $4.6 million. Which one is he going to get would depend on the fly that American Airlines would undertake. I'm sure you can see the matrix there. Now, first, let us see whether there is a dominant strategy for each player. Let's check whether American Airlines has got a dominant strategy. This is how you check it. If United Airlines should fly 96, which strategy do you think American Airlines is going to fly? Check it. If United Airlines should fly 96 strategy, which strategy do you think American Airlines will fly? Who can tell me? And of course, you can tell me that based on the payoff. Who's going to tell me that? Which strategy? Francis. Yes, Francis. American
on the payoff.
Just tell me the strategy. We'll look at the explanation later.
That is that is 4.6.
I said the strategy. You're not getting the point. Give me the strategy, not the payoff.
Okay, QA equal to 48.
Just say 48. You see, you're confusing yourself. Okay. They'll go for 48 because I know once you mention they'll go for 48, I know it is because you are using 4.6, which is more than the 3.1, which is more than the 0. Okay, so 4.6 is the one that will give them the highest payoff, and that's why they will fly 48. Okay, so 48. Let's see whether they will maintain the strategy if United Airlines should change from the 96 to 64. If United changes from 96 to 64, which strategy do you think American Airlines will go for? Which strategy? Stephen Covey. Stephen, which strategy do you think, Stephen, are you here? Which strategy do you think that American Airlines will go for? Yes, Miriam.
48.
48, that's it. They'll go for 48. And again, we all know that 48 is wrong. Why is 48 wrong? Oh, sorry. By the way, the first one, the ones I highlighted, okay, were wrong, but then the strategy was the same. I should have highlighted, remember, we are highlighting American Airlines. So I should have highlighted 2.0, but the strategy will still be 48, okay, because 2.3 was more than 2.0. It was more than 2.0 and 2.3 was more than 2.0. And now my next question is that if United Airlines should go for 64, what will American Airlines go, Francis? Francis?
64.
They'll go for 64. See, if a United should go for 64, American will go for 64. Why? Because look at it. If Americans should go for 96, they'll get 3.1. If they go for 64, they'll go 4.1. If they go for 48, they'll get 3.8. Which of them is the highest? Is a 4.1. So they'll go for 64. So do you realize that American Airlines has changed its strategy? Previously, it was going for 48. Now that United Airlines changed, American has changed to 64. So American has no dominant strategy. Do you guys get it? If you get it, you let me know. If you don't get it, you let me know, because then that's the only way I can repeat it. Okay. Now let's go to American. So we now know that American Airlines has no dominant strategy. Let's see United. Let's see United. Now, American go for 96. United will go for what? Now we are looking at the columns. American goes for 96. United will go for what?
48.
48. Because 2.3 is more than 2.0 and more than 0. Fantastic, 48. If American should go for 64, United will go for what?
64.
You will also go for 64. So it's also changed its strategy. So on the basis of this, would you say United and American have got a dominant strategy? No. None has a dominant strategy. Fana. So we can't use a dominant strategy approach to arrive at a pure strategy Nash equilibrium. Now, what do we use? There are two approaches we can use. One, we can use iterative elimination of strictly dominated strategy. And now you got to follow me to know how that is done. Remember, dominated strategy. So let's start. So that means that we're going to cancel some of the strategy. We're going to kill them. So let's start with American Airlines. Sorry, United. United go for 96. Watch. We concluded that American will go for 48. Do you remember? Do you remember? United go for 96. We concluded American will go for 48. Do you remember?
Yes, sir.
Yes, sir.
Okay,
Yes.
now watch something. Because we have concluded that American is going for 48, what do you think we'll do to Americans 64 here and 96 here? We'll destroy them. Because they are dominated. Remember, the iterative elimination, eliminating the strictly dominated strategy. We are eliminating the strictly dominated. And why do we say they are dominated? Because if you look at the 48, the 2.3 is more than the 2.0, and it is more than the 0. And so we can cancel the 96 and then the 64. Do you guys get it?
Sir, please take that again.
American goes for 96. Sorry, United goes for 96. American can go for 96 or 64 or 48. Which one should he go for? You go for 48. If he goes for 48, then we are saying that this one is dominated. But that is not so. The only way you can cancel these things fully is that it must be strictly dominated. Strictly. Now, what do we mean by strictly? So watch 48. So this is how you're going to do it. Watch 48, watch 64, and watch 96. And look at the numbers. 2.3 is a champion of all of them. So 48 will win in the first row. Now, in the second row, when United go for 64, look at it, 3.8. And then 4.1. You can see that the 3.8 is not more than the 4.1. Even though the 3.8, even though this 3.8 is more than the 3.1, it's not more than the 4.1. So you cannot cancel 4.1 to make it look like 3.8 is bigger than 4.1. You cannot. And then when you go to the third one, okay, 48, you can see that 4.6 is not more than 5.1. And it is even the same as 4.6. So what you are going to do now is that you're going to compare the strategies one by one. Between this strategy and this strategy, not all of them at a go. So this is how you start. Let's compare strategy 96 and 64. Does 96 strictly dominate 64 in all respects? Well, check this. For American Airlines. Does 96 dominate? No. Only if you look at it, 2 is bigger than 0. 4.1 is bigger than 3.1. 5.1 is bigger than 4.6. So we can conclude that QA, and watch the way I'm going to write it, QA64 strictly dominates, and this is the way we write it, not greater than by life, strictly dominates QA96. Do you guys see that? When you compare the payoffs, you see that strictly all the QA64 are bigger than the QA96. You see that? Strictly speaking. Christabel, do you see that?
Yes, please.
So on the basis, which of the two strategies is dominated? 96 and 64, which one is dominated? Strictly.
96.
96. So on the basis of that, as far as that guy is concerned, 96 will go. Okay. So this is how you do it, knowing very well, and this is how you've written it, knowing very well that that's the case. We can cancel this 96. That strategy is gone. This strategy is gone. This strategy is gone. In the world of that American Airlines, it's gone, and I mean it's gone. But we can't do anything yet with 64 and 48, because if you look at 64 and 48, you see 64 strictly dominates 96. We have established that. But what about 64 and 48? Well, you can see that 48 is bigger than 64 in some respect. 64 is also bigger than 48 in some respect. So we can't cancel those. Or we can cancel 98 for American Airlines. For American Airlines. Let's go to United. Let's go to United. United, now already remember that already that whole column is gone. So as far as United is concerned, this column is not even there. It's not there. You can't even look at it. So United is going to start with these ones. So United go for 96. So check 96 for United. Check this 96 for United, and then 64 for United. Looking at their payoffs, which one is strictly dominated? 96 and 64. Which one? And I'm on this part here, and that part here.
96.
96 is strictly dominated. Why? Because 4.1 is bigger than 2. Sorry, 4.1 is bigger than 3.1. Okay. And then 5.1 is also bigger than 4.6. So these ones show that Q64 strictly dominate Q96. So on the basis of that, you come back here, okay, and then you can now write that for United, okay, which is now QU. So QU64 strictly dominates QU96. So on the basis of that, we can cancel this one too. This whole 10 years is gone. It's gone. We can cancel that, okay, by using. So sometimes you have to redraw them. It's gone. So what are we left with? We are left with that small corner here. If you are following, you will notice that, okay, we are left with just this small corner here. Those are the values that we are left with now. We are left with these values to work with. So you can rewrite them and then still continue with your domination. Let's rewrite them. Okay, let's rewrite them. Okay, so we are left with this. If you check the slides, you see most of these things. Okay? All the things I've explained, they're all here. 64 strictly dominates, 48, all of that. I could ask you strict and weak domination, but I want to do the strict one first. You will know that some of them are not. So look at the blue ones. The blue ones are what is available now. So now that we have these blue ones, 64, 48, 64, 48, let's try to use the strict domination again and see. So let's go to 64 and 48. If you check 64 and 48 for American, those are the numbers. 64 and 48, check. 64 and 48. So you are checking this number, 41 and 38. You can see that 64 is winning. You check 5.1 and then 4.6. Again, which one is winning?
64.
64.
64.
So at that small corner point here, you can see that 64 dominates 48. You can see that 64 dominates 48 in all respect. So what should we do? We will cancel this whole column. We'll cancel it. And now we are left with what? We are left with only this. And now we have to go and ask United and compare United too. So now United, 64 and 48. United is battling between 4.1 and 6.8. So which one will be canceled under United? 64 or 48? Under United, which one will be canceled? Strategy 64 or 48? If you look 48. At the pair, 48. So we will cancel this 48. Finish. Therefore, our final thing is that we are left with QU 64 and then QA 64. And that gives us a payoff of what? $4.1 million. So using the iterative elimination of strictly dominated strategy, we have been able to arrive at the pure strategy Nash equilibrium. The pure strategy. So what we're doing is that we're canceling the strategies. We're canceling the strategies. And then when we got to where we got to, we cancel them again using what is left. And then you arrive at it. So this is one way. Remember, I was using strictly domination. Strict domination is what you will use. We could have used weakly domination. If I would have realized that some of them were weakly dominated, but we can't use weak domination to cancel. Okay. Let me give you just one of the weak domination. Okay. Just one of the weak domination here. Okay. Let me just go back to the original. Weak domination. I just want to show you how to identify weak domination. Okay. Just look at this. Now, if you look at between, even in this big space, all right, between 64 and 48, watch something. You will notice that, watch it, 2.1, and I'm talking about American Airlines, 2.1 is bigger than 2.0, but 3.8 is not bigger than 4.0, so there's no domination there. But let's compare 96 and 64. 96 and 64. You will see that 96 and 64, 64 strictly dominated 96. But let's compare 96 and 48. 96 and 48 for American. You will notice that 2.3 is more than 0. 3.8 is more than 3.1. But 4.6 is the same as 4.6. Do you realize that? Do you realize that?
Yes.
So on the basis of that, we can say that strategy 48 weakly dominates strategy 96. Why weakly? Why weakly instead of strictly? Because the last one, they were the same. 4.6, 4.6 for American. 4.6, 4.6. And because it is not strictly bigger, the 4.6 and the 48 is not strictly bigger than 4.6 and the 96. That is why we say that is weakly dominated. I'm showing you just this one weakly domination for you to note that sometimes you can be asked to identify all weakly dominated strategies and identify all strictly dominated strategies. That's it. Now we are done. We have seen how you can use iterative elimination of strictly dominated strategies to solve for this final answer. Now, what other approach could you have used? You could have used an approach which is known as the best response strategy. The best response strategy. And I'm going to show that using that same one to solve this finally, and that will be the end. Watch me. So that one you cancel. Watch me carefully how I show that final one. Now, best response strategy is this. You ask yourself that if United go for 96, what would be the best response strategy for American? Who can tell us?
48.
48. So now let's circle the payoff. So now you circle the payoff. Which payoff should we circle?
4.6.
No. Which payoff for American should we circle?
2.3.
2.3, that's it. So if United should go for 96, American payoff that will go for is 2.3. Let's go to the next one. If United go for 64, American payoff that he will circle is what?
4.1.
4.1, very good, you circle it. If United go for 48, America's best response will be what?
5.1.
5.1, fantastic. You are done with American. Now let's go to United. If American goes for 96, remember we are now looking at United. United will go for which best response? Payoff.
48.
I say payoff.
2.3.
2.3. See, now we are talking about the payoff. Okay. And if American goes for 64, United will go for what?
4.1.
4.1. If American goes for 48, United will go for what?
5.1.
5.1. So we have been able to do all of them. That's it. And once you see anyone that has two circles, that is a pure strategy, Nash. Do you see that this best response approach is easier? Or you don't see?
And faster.
And faster. So on the basis of that, the best response strategy will be the one with the 4.1, 4.1. That is how you do the best response approach. So the best response approach, you are circling the payoffs. By the iterative elimination, you are eliminating the strategies. Take note. Iterative elimination, you are eliminating the strategies. At the best response, you are circling the payoffs. And at the end of the day, the payoffs that are doubly circled in one box, that one is the final answer for the pure strategy. So when you see the notes, okay, that one is easy. I mean, you see, we just finished right now. When you see the notes, you see I've got some examples for you, okay, for you to look at. Let me see whether you can be able to do this one quickly. Look at this first one, player 1 and player 2. Let's use the best response, okay, best response to see whether you can crack this one for game 1. So if player 1 goes for A, player 2 will go for what? If player 1 goes for A, okay, which best response payoff will player 2 go for?
X.
5.
The number, we want the number.
5.
5, good. Let's circle the 5. If he goes for B, what is the best response payoff for player 2?
4. No, 3.
It's 3. Remember, okay, it is the second number we are looking for. If he goes for C, player 1 goes for C, what is the best response payoff for player 2?
5.
5, good. Now we circled. Now let's go to player 2. If player 2 goes for X, what is the best response payoff for player 1?
5.
5, so we circle the 5. If he goes for Y, what is the best response for player 1?
3.
Circle the 3. If he goes for Z, what is the best response for player 1?
5.
Therefore, our pure strategy Nash equilibrium using the best response approach is what? B and Y, which gives us 3 and 3. So this is how you write it, okay? The best response is BY, which gives us a payoff of 3 and 3. That's it. Go and use the same best response approach to do the other one here. And you will see how enjoyable and fun it is. Okay? Use the same best response approach to do the other one. And you will see how enjoyable it is. Of course, I have another example for you where you use both the iterative elimination approach and then the best response approach for this very example. And you'll be fine. This is all. This is all. Let me summarize. Try and understand how to, when you have a story, how to identify the players, the strategies, the payoffs, how to draw the thing in the payoff matrix or the box or the strategic form, sometimes called a normal form, and how to draw it, identify all the things nicely, how to identify whether there is each player has a dominant strategy or not. Okay. And if they have a dominant strategy, that will lead to a dominant strategy equilibrium. Identify that. Okay, the next one, if they don't have a dominant strategy, how to use the iterative elimination of strictly or weakly dominated strategy. You have to mention that word very quickly. How to use, but I will never ask you to use a weakly dominated strategy to find the equilibrium. You need a strictly dominated strategy. But I can ask you to tell me which strategies are weakly dominated and which are strictly dominated. And then finally, how to use the best response approach to arrive at the final answer.
So we are here.
Are you beginning to enjoy the game theory? This is the basics of game theory for your level for now. Are you beginning to enjoy the game theory?
Yes, it's nice.
If you didn't enjoy it, go and look at some of the examples. You will love it. I'm telling you, you will love it. Okay. Anyway, so that brings us to the end of the entire caboodle. Okay, we are going to meet again, and then we'll look at another topic. But this is it. So you need to be able to, find out all of this, and then identify 3 things: whether the content, the outcomes are Pareto optimal, whether it's a zero-sum game, or whether it's a president's dilemma. These 3 things, note: Pareto optimal, zero-sum game, or president's dilemma type. And when you go through all of this, you'll be able to get it. So thank you very much indeed for your time. Have a wonderful day. If there is any question, you can ask me now.